Hello everyone, welcome to this first supplementary session to complement the mechanics lectures that you're doing in first year physics at the University of Leeds. I know you're doing maths as a separate module at the moment, but this is just a supplementary thing with a specific focus on mechanics and what you'll be learning with me in mechanics 1. So in this session we'll be doing vectors, in the next session we'll be doing calculus, maybe going forward from there I'll do some more, but we'll see. If you happen to just be watching this on YouTube because it's publicly available, welcome. So let's learn about vectors, but in the context of mechanics. So what we're going to be learning, or recapping if you've done some of this before, is what a vector is. So we're going to think about what a vector is, how to represent a vector, whether mathematically or in a diagram, how to use vectors and scalars, which are just numbers with units attached, to represent physical properties. And we're also going to learn how to mathematically combine vectors and scalars together. So by combine, I mean add, subtract, multiply, that sort of thing. So by the end of this, if you listen along and work through the tasks and do some of your own, you'll be able to represent appropriate physical quantities using vectors in 3 different ways. So you'll know from previous studies probably that certain things in physics are vectors, not just numbers, but vectors. We'll learn what that means. But in addition to that, we'll learn how to manipulate them mathematically, which isn't always done so rigorously at school, but is needed at university level physics. So we'll learn how to perform fundamental operations using vectors. So in this session, we're doing addition, subtraction, multiplication. We might do one more session on vectors where we'll do a bit of extra stuff. And we're also going to derive the formula for calculating the vector dot product. So derivations of this sort of thing, usually left to the mathematicians. But it turns out that learning how to derive the formula for calculating the dot product is a really useful thing for physics intuition. So we're going to do that as well. So first, before we even do any of that, let's think about mechanics. This is the context that we're coming in with to look at vectors. So mechanics is the study of motion. So how things move, how things get from one place to another place in 3-dimensional space. 3 dimensions is probably going to mean vectors, an x, y, z. How fast it gets there, and also maybe acceleration as well. Turns out that mechanics is the beginning of all human knowledge of physics. When humans first started making civilization, we probably looked out the window and thought, that's moving, that's weird, why is it moving? And those sorts of questions lead to the development of other areas of physics. In fact, it turns out that in physics in general, we can know about a position of a thing, a velocity of a thing, and if we know those 2 things, we know basically everything about the system. So, the beginning of all physics. Turns out that mechanics is the fundamental source of metaphorical understanding in physics. I'm not even going to get into that, but if you're interested in philosophy of physics, grab me after a lecture, we'll talk about it. But from there, with that mechanics, with that motion in mind, we'll move into vectors. Let's do this. So here's a quote. The main conceptual hurdle of first year university physics is applying vectors and calculus to physics problems. Who said that? Probably every physics lecturer in the world. It turns out that that is one of the biggest things that we need to get over in first year, and that's what I'm going to try and help you with today. Taking that idea of a vector that you've learned in maths and applying it to physics problems. Thinking about physics concepts in terms of vectors as well as scalars. So what even is a vector? So we've mentioned this word vector, we've mentioned this word scalar. We've probably heard of these things before, and we've come up with a few examples before. So just before I click through these slides, take a minute, 30 seconds or so, to come up with some examples of scalars that you might have heard of before. I'm not going to wait for that amount of time, by the way. You can pause this recording and then replay when you want to continue. So take 30 seconds to a minute, think up some examples of some scalars. Importantly, what units do those scalars have? Okay, So my examples that I've got, and this is not an exhaustive list, but my examples are temperature, which has units of degrees Celsius, degrees Fahrenheit, or Kelvin is what you'll commonly use in physics. Charge, which has units of, is it coulombs? Or is that current? Current's coulombs. Charge is coulombs. Charge has units of coulombs. Current has units of amps, that's the one. So charge has units of coulombs. Wavelength, that's a length, so that's going to have units of meters. Distance, that's going to have units of meters, probably. Speed, so that's how many meters we cover per second. That's going to have units of meters per second, perhaps. Acceleration, how many meters per second are we going over every second? How does our meters per second change every second? Meters per second, meters per second squared are the units for acceleration. So now we've got a general idea of what a scalar might be. It's a number, right? A number, just a number with units attached, potentially, in physics, with units attached. So the same thing again. Take 30 seconds. Come up with some ideas for vectors. Some things that are vector quantities that you might have heard of before. Or maybe have a guess at some things that you think should be vectors. Okay, so take 30 seconds for that. Okay, what examples have I got? Here we go. Force, you might have heard of. Force is a vector. It has a direction. I can apply a force to something in a certain direction. I can apply it in another direction. Same strength of force, different direction, so it's a vector. Torque is another vector, it turns out. We'll do this in mechanics. In circular motion is when we'll think about torque. But if you've ever done moments before, force in one direction times distance in the other direction, that is an approximation of a more general concept to do with something called torque. You might have heard of torque in terms of cars, which is to do with how much force is required to make the wheels spin. Torque is a vector, and it's an important one. The wave vector, k. So the wave vector is related to the wavelength, because I can have a wave going in this direction, I can have a wave going in this direction. They might all have the same wavelength, same length in every direction, but different direction. So wave vector tells us something about how long, how short, what frequency that wave has, but also what direction it's moving in. So a wave vector is also a vector. Displacement is the vector equivalent of a distance, roughly speaking. So displacement tells us about how far we've moved from a certain point. So if we move from here to here, that's a displacement here. That's a displacement here. Well, that's a displacement as well. It's a vector of length 0. So displacement tells us something about distance, but also with a direction involved. Velocity, again, speed with a direction. You can go in a speed in any different direction. Acceleration, same as acceleration, but with a direction attached. So we can get a general version of this now. It's a one-dimensional collection of numbers. And by one-dimensional, I don't mean it's one-dimensional as in like 1D. You can have something in that direction, something in that direction, something in that direction, 3 dimensions represented by a vector. But what I mean by a one-dimensional collection of numbers is I mean it's a list of numbers, right? If you've got a vector and you put it in column form, it's just a list of numbers, right? So a vector is a one-dimensional collection of numbers, a list of numbers, and it can represent objects in 3 physical dimensions. Bit confusing, but this is a number, scalars are a number. Vectors are a list of numbers. Matrices. Some of you, if you've ever done further maths, might have come across matrices before, and you'll have learned really, really weird ways of times them together and how they multiply and weird things about the determinant, and it's all very complicated. As part of your physics degree, you'll learn what matrices are actually used for, what calculations they can be used for, specifically in continuum mechanics and quantum mechanics. Matrices are really, really important. We're not going to cover them here, so I'll just go down the list really quickly. Stress, which you might have come across before, is actually a matrix. Strain is a matrix. That might suggest that the Young's modulus is also a matrix. Interesting. Boost is a matrix. It's to do with relativity. And electromagnetic matrix. The electromagnetic matrix, F tells us something about how electric and magnetic forces combine together in a really neat form. That's also a matrix. But don't worry about it right now. Don't have to worry about it right now. We're going to stop at vectors. But a matrix is not just a list of numbers. It's a square of numbers. Those of you who've come across it before will see a matrix represented as a square. So it's a square of numbers, and that square structure is important. So it's a two-dimensional collection of numbers. I've left a gap here for things called tensors. Not even going to get into that, but there's something called the Ricci tensor, rotation tensor or matrix, a transformation tensor, a general operator L tensor. That is an arbitrary dimensional connection. I'm not even going to get into that. It's really complicated. That's fourth year stuff. So if you're really interested in this, stick around for 3 or 4 years and we'll teach you about it. But for now, we'll stop at vectors. But we've got this idea that we've got a number and a list of numbers. Scalars then have size only and units. Vectors have both size and direction. That's super important. A vector has a length, a size, an amount, and it points in a specific direction, which tells us something else about that object. It tells us about how it's oriented in space. That's super interesting. So here's some examples of vectors, right? How can we represent this vector? Take 15 seconds to think about how we might draw a force on a piece of paper, or how we might write a vector out algebraically on a piece of paper. 15 seconds or so to refresh our memory on that. Diagram. Diagram is the best way, and I'm not joking, for the rest of your physics degree. It's not just because they're worth a mark apiece. It's the other way around. We give marks for diagrams because they're so important in how you represent and understand a physical system. So the best way to represent a vector, in my opinion, is a diagram. Here's a vector on a diagram, right? 2 points and a line between them. I've called it V with a little line underneath it, right? That tells me it's a vector, a little single line underneath it. And in fact, its size is the length of that vector. And its direction is 1, 2, 3, 4 in that direction and 2 in that direction. So 4 across and 2 up. That is the direction of that vector, right? So it's got a size and it's got a direction. We can represent that vector in terms of what are called basis vectors, unit vectors. We'll get onto them shortly. But I can say that this vector V, which has a length in that direction, is A units in that direction plus B units in that direction. So we can add vectors together, as we'll see shortly. And so that gives us the ability to write it as a column vector, right? We can say that V, the vector, is A in that direction and B in that direction. A in the X direction, represented by the vector I, and B in the Y direction, represented by the vector J. And so we can just write that as a column vector, right? A, B. A, B, kind of like coordinates, but a bit different. And if we had a three-dimensional position vector, we might say it's X in the X direction, Y in the Y direction, Z in the Z direction. So that is a three-dimensional vector. So it's got 3 components, 3 scalars make up that vector. This one is a two-dimensional one, so 2 components or 2 scalars make up that vector. And the final way we can write it down is purely algebraically, and this is going to become really important when we start doing calculus and things like that. So algebraically, I can say that V, just like we described at the start, is A times a little bit of the X direction, or the I vector, plus B times a little bit of the Y direction, or the J vector. R then is X times I plus Y times J plus Z times K. These I, J's and things are important vectors. We'll get onto them shortly, what they are, what they mean. But for now, these are the three ways that you can write out vectors. But at the end of the day, whatever way we choose to represent these vectors, let's take V. V is that arrow there. That's one representation of it. V is exactly equal to this column vector. V is exactly equal to AI plus BJ. These representations are all exactly the same. We can equal them to each other. A vector is basically, you can imagine it as an arrow. That's it. It's an arrow, and we are trying to describe that arrow. It has some length and some direction, and with those things we can describe that arrow. And each one of these vectors can be described in exactly that way. A force is some size pointing in a direction. A wave vector is moving in some direction and it has some wavelength, things like this. So what properties do vectors have? We've discussed a few of them. But they have a magnitude, they have a size. So here, V, we can work out its size, can we not? Because we know that it's A across in the X direction and B up in the Y direction. That's a right angle triangle. Cartesian coordinates make that easy for us. We can make a right angle triangle out of this. So we can say that the magnitude, the length of that line is what? I'll give you 10 seconds on that. Actually, you can take as long as you want, can't you? You can unpause the video whenever you like. Take as long as you want. The magnitude of that vector we can get from Pythagoras' theorem, right? It's A across in this direction, and it's B up in that direction. A squared plus B squared equals the length of that squared. So the magnitude, the size of that vector, which we represent by putting two lines either side of the vector symbol, the magnitude of that vector is the square root of A squared plus B squared. Easy. Easy if you know Pythagoras' theorem. In 3 dimensions, it turns out, it's the square root of x squared plus y squared plus z squared. In 4 dimensions, it's x squared plus y squared plus z squared plus the next one squared. You can prove that it's always the sum of squares if you're interested in however many dimensions you have. But we really only need to care about 2 dimensions, 3 dimensions, and if we did 1 dimension, it'd be the square root of a squared, which is just a, easy in 1 dimension. This vector here also has an angle, and we can describe it by that angle, right? The angle it makes with the x-axis. That's another way of representing the direction, right? Because I can say a vector has some length in the x direction and some angle of rotation, and that will take me to the same place. In fact, that's a coordinate system called circular coordinates. We'll get onto that at some point during the first semester of learning mechanics. But for now, let's just think about what this angle is. Let's do some more trigonometry. The sine of that angle is opposite over hypotenuse. So sine theta is b divided by the magnitude of v. That's one way of getting the angle. But the more common way is to use the x direction. So the cosine, the cos of that angle, is a divided by the length or magnitude of v. That's the cos. We can combine those things together and find out that actually it's the inverse, well, the tan of the angle is opposite over adjacent, right? So you can either do it, if you know the length of the thing, you can do cos or you can do sine. But if you don't know the length of the vector, you just know the components, then you can say it's the inverse tangent or the arc tangent of opposite divided by adjacent, b divided by a. Interesting. Turns out that the angle in spherical coordinates or 3 dimensions is a bit more complicated. There are actually 2 angles that you need to do the same thing in 3 dimensions. So don't worry about that for now. Google spherical coordinates and look at the Wikipedia page if you really want. But we'll talk about this more explicitly when we do spherical coordinates, probably in quantum mechanics at some point. But in general, vectors need as many numbers to define them as there are dimensions to describe. So in 2 dimensions, we need a and b. In 3 dimensions, we need x, y, and z, a, b, and c, whatever you like. But we can also use the magnitude and the angle instead. So 2 dimensions, we need the length of the thing and the angle it comes round to. In 3 dimensions, we need the length of the thing, 1 angle, and then another angle to find us a position in 3-dimensional space. So we need 3 numbers because we're in 3D, 2 numbers in 2D, so on and so on. So that's going to bring us on to the idea of a unit vector. A unit vector, what is that? We've already seen 2 of them, it turns out. 3 of them, in fact. But we're going to think about this in a more general idea now. A unit vector is a special type of vector where the magnitude of that vector is exactly equal to 1. Oops. I, j, and k are therefore unit vectors in the directions of x, y, and z. But any vector can be a unit vector. We'll get onto that shortly. But if a vector has a magnitude of exactly 1, what that means is a unit vector is almost like a representation of a pure direction. There is no size. It's not size 0, it's size 1. Because whenever I multiply that vector by its size, it becomes that size. So a unit vector is almost like a direction. And then when you multiply it by the size or the magnitude, you get the full vector. So size times direction equals a full vector. And a unit vector is that pure direction. So therefore, when we say AI plus BJ, we're saying, okay, it's a size, an amount in the x direction multiplied by the x direction, I, plus an amount in the y direction multiplied by the direction itself, j, k, in general, though, because we can make any vector into a unit vector, right? I can put something in this direction and make it, scale it down so that it has size of 1 instead of size of whatever it had before. I can make any vector a unit vector. And in that case, it's usually given a hat, like a little hat symbol. So if v is some vector, any vector, not I, j, and k now, but literally any vector in any direction, v hat is the unit vector corresponding to that vector. So imagine some vector, if I scale it down so that its length is 1 or its magnitude is 1, that's a unit vector. Same direction though. So therefore, to calculate a unit vector, we just divide the vector by its magnitude, right? Whatever its magnitude is, take that vector, divide it by it, and it'll have a magnitude of 1. That's how you find a unit vector. And that's in any direction, right? R hat means it's pointing in any direction. So here's a diagram, check it out. Here's v, some vector. It's 3 in the x direction, or 3i, 4 in the y direction, or 4j. So if you know your Pythagorean triples, you might know that this is of length 5. 3, 4, 5. So the magnitude of this vector is 5. So if I want the unit vector, I'm going to have to scale everything down by 5. This is going to have to be 3 divided by 5. That's going to have to be 4 divided by 5. So let's do that. 3 divided by 5. 4 divided by 5, square that, add them together, take the square root, and you'll find that the length of this is 1. So that's the vector, and that's the unit vector. Just divide each component by the magnitude, no problem. So that is enough now to bring us on to a little task that I want you to do. I'm going to go through the task. But I really want you to do these things at home. It'll take you like, I don't know, 15 minutes or something like that, but it's really worth practicing. You learn best via doing, and that's not just a learning style. Literally everyone learns better by doing because you learn it by rote, you learn it by practice, just like a sport, just like anything. So don't just listen to me solve this problem like a YouTube video to listen to for lo-fi's sake. No, do this task yourself. Have a go at it. A force is acting on an object, right? So just imagine an object in your head. Imagine a force is acting on it. The object is at position x equals 2, y equals 3, z equals -1 meters. And the force is 3 newtons in the x direction, -4 newtons in the y direction, and 0 newtons in the z direction. The task is to represent both of these vectors on a diagram using each of the 3 methods that we've discussed. So represent those 2 vectors on a diagram algebraically and as column vectors. So that's your task. I'll give you 10 or 15. Well, you can take as long as you want. 10 or 15 minutes, though, is how much time I reckon this will take. Okay, let's do this. So, first things first, column vector. It's 2 meters in the x direction, so 2's in that first one. 3 meters in the y direction, and minus 1 meter in the z direction. Nice. And force is 3 newtons, minus 4 newtons, and 0 newtons. So that's easy, x, y, z, each component has been added in. Notice the lines underneath the things so that we know that it's a vector underneath the symbols, and notice the units. Units are important, keep them. So let's do it algebraically now. So here I've got 2 in the I direction plus 3 in the j direction and minus 1 in the k direction, and I've just factored the units out. It just looked nicer to write it that way, to be honest. You don't have to. You can keep them in like this, but I just factored it out. So it's a vector times by some units, but you don't have to do that. F then, the force, is 3 in the x direction, minus 4 in the y direction. We don't need to put 0k in the z direction because 0 times something is 0, so let's get rid of it. And then newtons again has come out of those brackets. So maybe it's easier to write it algebraically, right? Because I've had to write 0n here, because if you've got a column vector, you have to put something in every column, otherwise it doesn't make sense. If I didn't put something in that third column, it would look like a 2-dimensional object, and it's not. So I have to put something in that column to make everyone realise that it's 3-dimensional. Whereas here, as algebra, I don't need to do that, because it actually doesn't matter whether or not it's 2-dimensional or 3-dimensional in an algebraic form. The maths will all work out the same. Diagrammatically, though, I'd be interested to see what you guys all got, but I got this. So I tried to draw my 3-dimensional axes, which is hard. It's very hard. I've drawn 3 and 2 in the x and y direction, but minus 1 in the z direction. It's hard to draw, but I've got a good go at it, right? It's 2 across in the x direction, 3 up in the y direction, and I'm imagining that it's come forward a bit in the z direction. And then because the force is acting on the object, I've put that force vector on the end, just as a notation for myself. And that is going 3 along in the I, minus 4 in the j. But it's not to scale. So personally, I think that these vectors here are quite hard to represent on a diagram. You get an idea that the force is in a different direction to the position vector, but the scales are all wrong and it's hard to do the third dimension and that sort of stuff. So I added in the algebra on the side for myself, just so that I knew what this diagram meant. And that's really important too. So I've used the algebraic form and the diagrammatic form. Generally speaking, I use these two when I'm doing vectors. So just think to yourself, which was the easiest representation? If I was to suggest a representation for you guys going forwards, I would suggest that first, the most important one is probably equal between algebra and diagram. So if you currently use column vectors, take some effort to learn how to write these things down algebraically, because it makes all the maths you do with vectors a lot easier to write it down algebraically. And a diagram's always good so you can visualize what you're doing. But when you start moving into things that require matrices, this is second and third year quantum mechanics, things like this, the column vector notation becomes important again. So these two for now, if I were you. Column vectors, keep them in your mind, but you won't need them so much going forwards. So now we can represent vectors, right? What can we do with them? Because it's all well and good to draw arrows all over the place, but what can we do with them? We can add them, right? So we can add numbers, scalars, we can add vectors. And that's going to be important. So I'm going to write this down here each time so we know what's going into this operation and what's coming out of it. In this case, I'm going to add some vectors together and I'm going to get a vector out of it. So 2 vectors gives you another vector. Vectors in, vectors out. That won't always be the case. So that's why I'm writing this down. So if I've got column vector, x1, y1, z1, x2, y2, z2, where the subscripts are just so we know which vector it is, the first one and the second one, then to add them together, I just do x1 plus x2, y1 plus y2, z1 plus z2. Just add the components together, right? Algebra, here we go. We've got x1 lots of I, y1 lots of j, z1 lots of k, plus, same thing for x2. If you take x1 and x2 and factor out that I vector, you'll see that it's x1 plus x2 lots of I, plus y1 plus y2 lots of j, plus z1 plus z2 lots of k. And that's why we can write it like this, because the algebra works out that way. Just add the components together. And if we do that, if we just add the components together, this is what it looks like on a diagram, right? So if I've got some R1 vector here and some R2 vector here, R1 plus R2 is like going from the start point of vector R1 to the end point of vector R2. And that's true for as many vectors as you want to add together. So if I added another one, R1 plus R2 plus R3, then the total vector would be the start to the end. It's just like following a path. That's exactly how vectors work. So this is called like the parallelohedron rule or parallelogram rule or something like that. But it doesn't really matter. It's basically about following the path. The vector R1 means I'm going from here to here. The vector R2 means I'm going from here to here. So if I add them together, it's like doing the whole thing in one step. There to there. So here's a little thing. We can add scalars together, right? Scalar added to scalar we can do, no problem. Vector added to vector we can do, no problem. But we cannot add a scalar to a vector or a vector to a scalar. That would make no sense. If we think about it, if I have a force and that force is going in this direction, and then I say, oh, there's another force of 5 newtons. How could I add those together? You need the direction to be able to say, okay, how does this force and that force affect each other? Because if there's a force of 5 in that direction and a force in this direction, they'll cancel out. If they're in the same direction, they'll add together. We need these things to have a direction as well as a magnitude or a size. So you can't just add a scalar to a vector. But you can add scalars to scalars and vectors to vectors. Nice. Vector subtraction then, because subtraction is basically just addition. It's the same thing, but framed differently. Same again, vectors in, vectors out. Column vector is just take the components away from one another. The algebra shows why this is true. x1 minus x2, factor out the I, and you get x1 minus x2 lots of I, y1 minus y2 lots. You get the same thing. So addition and subtraction, inverse operations, but the rules are very, very similar to one another. Just subtract the components. Diagrammatically though, it's a little bit trickier to contemplate what it means to take a vector from another vector. So I'm going to take you through 2 ways of thinking about this. So the first way I'm going to suggest is that we start here, right? That's R1, so I'm adding R1. And then the vector is in this direction. So I'm adding R1, and then I'm adding R2 minus R1. So R1 add R2 minus R1 equals R2. So if I do the addition operation along this path, we get the vector R2 out. So this must be R2 minus R1. That's one way of thinking about it, right? If I do R1 add R2 minus R1, I get R2. So this works out. So that's nice. A better way of thinking about this is if I've got one vector R1 and one vector R2, and I'm doing R2 minus R1, it's just between the endpoints, right? So from the end point of R1 to the end point of R2. Gives you R2 minus R1. That's another way of thinking about it. That's quite an important way of thinking about it when you come to electromagnetism, because a charged particle might have a position vector, and another charged particle might have a position vector. Those two charged particles are going to interact somehow. They're going to attract or repel each other. And so that vector is going to be the important one. So R2 minus R1 is the end of R2, the end of R1 to the end of R2. And if I did R1 minus R2, that vector would just change its direction, multiplying by a minus sign effectively. So R1 minus R2 would start there and end there. Got it? Same as addition. Scalars, yes. Vectors, yes. But vectors and scalars, no. Makes no sense. How can you take away a size from something that has a direction? Unless that size also has a direction. Got to be rigorous with these things. So now we've done addition and subtraction. Obviously, the next thing to do is multiplication, right? Adding things. Vector multiplication. So if I multiply a vector by a scalar, does that make sense? Yes, it does. We can define it such that it makes sense. If I define a vector multiplied by a scalar such that it increases its magnitude by that scalar factor, it all works out well. So here I've got a vector and a scalar going in, because I'm going to times a vector by a scalar, and I'm going to get a vector out. So here's our little table for multiplications. It turns out that you can times a scalar by a scalar, no problem. You can times a vector by a vector, we'll get to that, but also you can times vectors by scalars, and that's what we're doing right now. So, column vector, if I am timesing a scalar c by x, y, and z, I just multiply it in like it's a big bracket. C times x, c times y, c times z. And algebraically, we'll see why that's the case. If I say c, open brackets, xi plus yj plus zk, close brackets, it's just like timesing out brackets. Each of these is a term. Just because it's a vector, it's still a term. So I can times c in by that, c times that, c times that. You get cx, cy, cz. That's your column vector. So you just multiply each component by the scalar. No problem. So here's a diagram, right? Here's R. It's 2 by 2. Nice. CR is now 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I must have multiplied it by the same number in both directions. And that number was 2.5, right? So C is 2.5, but in general, multiplying a vector by a scalar maintains the direction, just increases or decreases its length. So it changes the magnitude only. And you can prove that to yourself if you want. So that is enough to bring us on to a second task. A different representation is what I've called it. So here's your scenario. An object is at position x equals 9 meters, y equals 12 meters, and a force is acting on the object, and that's minus 3 newtons in the x direction and 3 newtons in the y direction. Oh, there's a typo there, I might fix that. So the tasks are to write down the position vector of the object r and the force vector acting on the object f. So we can do that. What are the x and y components of each vector? So just remind yourself of that. Here's a little hint. And then the key now is calculate the unit vector and magnitude of both r and f. So that should take you, I don't know, maybe 15 minutes, half an hour, something like that. So give yourself some time and then unpause the video again. Okay, so let's write down the position vector of r. R is 9 in the I direction, 12 in the j direction. Meters are the units, I've just factored them out. No problem. I could have factored out another 3, right? So it'd be 3 lots of 3i plus 4j. It's exactly the same, but I like to have my vector components very readable. So I know that this is 9 in the I direction. I don't have to worry about multiplying out the brackets here. I'm just keeping it in that form. Makes working with matrices a lot easier, that is true. So f then is minus 3 in the I direction and 3 in the j direction. Again, I've factored out the units. Here, because it's the same in both directions, I have factored it out because it's clear that it's the same in every direction. That's the only time I ever factor numbers out of vectors myself. And it shows me that it's minus I and plus j directionally. I could have factored out minus 3 and got minus 3i minus j. Again, that's exactly the same, but I want to minimize the number of minus signs that I have, so I don't say, oh, I've got minus times minus times minus. I don't want to be timesing minuses together, so I've just taken 3 out and kept the minus in there. I could have said j minus I as well, if I wanted. So what are the x and y components of each vector? So here we've got r, so r underscore x is 9 meters, and r underscore y is 12 meters. So that subscript there is just there to tell me it's the component in that direction, right? Notice that it has units. F here is the same. So F in the x direction is minus 3. F in the y direction is 3 newtons. Notice those units. It turns out that scalars are the things that hold units. Magnitudes have units. Directions, the directional part, the unit vector part, if you like, doesn't have units. It's the scalar part that holds units. So components have units because they're scalars. Single numbers. 9 meters in the x direction. 12 meters in the y direction. That wouldn't make sense without units. Same with forces. It's minus 3 newtons in the x plus 3 in the y. So directions don't have units. It's the scalar components that have the units. That's important because units behave like algebra. So now I'm going to calculate the unit vectors and magnitudes of each vector. So I'll start with the magnitudes. So if I've got Rx equals 9 meters, Ry equals 12 meters, the magnitude of that vector then is 9 squared plus 12 squared raised to the power half, or square rooted. So that's 15 meters exactly. So that's nice. Pythagorean triple, it works out perfectly. The unit vector then is just 9 divided by 15 in the x direction and 12 divided by 15 in the y direction. So there's our unit vector. 3/5 I, 4/5 j. You'll notice that that has length 1. The force we can do exactly the same process, squared, squared, square rooted. We find that the force magnitude is approximately 4.24 meters. In physics, it's better to represent things not as perfect fractions or the weird fractions that scientific calculators spit out, but to 3 significant figures, 2 decimal places or 3 decimal places. Some level of accuracy that you stick to throughout your calculations. Because errors are really important. The amount of accuracy that we have is really important. So here I've used 3 significant figures and I'm going to stick to that. So to get the unit vector, I just divide that original vector by 4.24, the magnitude. So 3 divided by 4.24 is 0.708. Oh, that's not I plus j. That's minus I plus j. That's a typo. I'll fix that. 0.708 minus I plus j. Because it's just this divided by the magnitude. So double check, the unit vector should have a magnitude of 1. So this squared plus this squared square rooted should equal 1. 0.708 squared plus 0.708 squared square rooted should equal 1. And they do. So here's something interesting. I can write this vector algebraically as Rx in the I direction plus Ry in the j direction, which is this. That's an amount in the x direction multiplied by the unit vector, the x direction itself. Amount in the y direction multiplied by the y direction itself, or the unit vector in that direction. But I can also say, check this out. If unit vector equals vector divided by magnitude, then vector equals unit vector times magnitude. So I can just represent a vector by an amount in that direction multiplied by the direction, which is 15 times 3 on 5, I, plus 4 on 5, j. Because that was the magnitude of this vector, and that's the unit vector. But see, if I take out a factor of 15 here, it's exactly the same. This representation and this representation are exactly the same. They're just different representations of the same vector. That's just the r hat direction. It's just an arbitrary direction. So in general, a vector is a combination of a size and a direction, right? We can form a vector using a sum of components x, y, z, or we can just use the size and direction of that vector directly. So that's the magnitude and the direction of that vector. Use whichever's easiest. It turns out that in circular motion, where things are moving in circles, this representation is a lot easier than this representation, because this representation has trigonometry and cos theta and sine theta and all this stuff, whereas this representation has none of that. It's a lot easier to use this for circular motion. In fact, all those formulas that you learn for circular motion, like mv squared over r and all this sort of stuff, make a lot more sense in this representation. So I'll just leave you to ponder on that for now. But what's important is that both representations are exactly the same. It's the same vector in both cases. So the last thing we're going to do today is, well, for this session, is more vector operations. So we're going to do the dot product. So the dot product is a way of multiplying a vector to another vector in order to get a scalar. So vectors in, scalar out. Why would we do this, right? It's not entirely obvious how you multiply two arrows together, whereas multiplying two numbers together is a lot more conceptually obvious. If I've got 3 sets of 5 objects, then 3 times 5 gives me 15 in total. So multiplying scalars is conceptually very obvious. Multiplying vectors, less so. I'm going to take you through a conceptual understanding of what the dot product is and why we might need it in physics. So imagine we've literally just invented vectors. Not like invented them. We've just decided we need to have a way of representing arrows on paper, right? And we want an operation that's similar to scalar multiplication, right? Because that's the first step. We now have to times numbers together. So let's try and times vectors together in a same sort of way as we would times numbers together. We've already noticed that if you multiply a vector by a scalar, it just changes its length, increases it or decreases it. So to multiply two vectors together, we might first want to transform the vectors to be in the same direction and then just multiply their lengths together. Because then it's like multiplying two numbers together, right? Think about that. Here is the graphical representation of what the dot product really is. So if I've got a vector A and a vector B, and I want to do the dot product, or A dot B, multiplying these two vectors together and getting a scalar value out, I want to get the amount of A in the direction of B and then multiply the length of A, the length of that by the length of B. So I'm getting as much of A as is in that direction and then multiplying it by the length of B. So it's almost like collapsing the vector A onto a number line and then multiplying the lengths together. And so we've seen then that this length here, the amount of that vector in the direction of B is A, the length of A, multiplied by the cos of the angle between those vectors. So mod A cos B. And then I just want to multiply it by the length of B. So A dot B is the length of this vector times by the cosine of the angle between the vectors to get the amount of this vector in that direction, and then multiply it by the length of b, which it turns out is mod A mod B cos theta. That is the conceptual basis of the dot product. That is why it is like that, because we're getting the amount of one vector in the direction of the other, and then multiplying their lengths together. That's what we're doing, right? I'm going to flip this round now. Same vectors and angles, but I've just made it so that A is on the x-axis basically, and B is not on the x-axis. B is the other one. So I've just reflected it so that A is on the x-axis and B is now pointing up. Just to make the point that the amount of that vector in the direction of A is modulus B, length of B, times by the cos of the angle between those two vectors multiplied by the length of A. It's exactly the same, whichever way you do it. So A dot B is mod A, mod B, cos theta, and you can do A dot B and B dot A, and they're the same thing. So that's very much like scalar multiplication. A dot B, B dot A. So here we've got a couple of vital identities, right? So we've got A dot B is mod A, mod B, cos theta. We understand conceptually why we might want to do that now. They're the same in both directions. What is the dot product? The dot product between two vectors A and B is the projection of one vector into the direction of the other multiplied by the length of the other. It's proportional to the magnitude of both A and B and is thus analogous to scalar multiplication. Times in two vectors together, kind of like their scalars. So that's the dot product. As a column vector, we can find that xy, x1, y1, z1 dot x2, y2, z2 is equal to x1 times x2 plus y1 times y2 plus z1 times z2. Algebraically, we might be able to see why that is. If we times out these brackets exactly like normally timesing out brackets, we get x1i times x2i, x1i times y2j, x1i times z2k, blah, 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 blah. So we'll get I dot I, j dot j, k dot k, but we'll also get I dot j, I dot k, j dot I, j dot k. We'll get all the other ones. I, j, and k are at right angles to each other, so cos theta is 0. So if I and j are at right angles, anything that is x1 times y2, x1 times z2, that's going to be 0, because I dot j 0, I dot k 0, because they're at right angles. But I dot I, they're in the same direction. Cos theta equals 1, so that x1 times x2 stays. You get x1 times x2, y1 times y2, z1 times z2. Just multiply each pair of associated components and add them. Nice. So why do we need the dot product? So this is a task, take you 15 minutes or so, maybe 20. A force is acting on an object, and that's it. That's all we know. Imagine we can write that force as fx in the I direction, fy in the j direction, and fz in the k direction. Calculate f dot I, f dot j, and f dot k. Imagine we can write it as the magnitude times the direction. Calculate f dot f hat. And then, here's a vector that's got an actual components to it. Calculate how much of that vector is in each of these directions using the dot product. So have a read over these, and I'll give you, I don't know, as long as you need to do these. One second. The perils of filming from home. So if I calculate these things now, f dot I, well, the j dot I bit and the k dot I bit go to 0 because cos of the angle between them is 0. So f dot I just equals the x component, f dot j, the y component, f dot k, the k component. The dot product of a vector with a unit vector gives the component of that first vector in the direction of the unit vector. So you can see why that might be extremely important. If I've got a force in some weird direction and I want to know how much of that force points in the direction of, say, the ground, then I can do the dot product of that force in the direction of the ground. That's going to be important for, say, dragging something along a surface or picking something up against the force of gravity. The dot product is going to be really important there. So now imagine we can write the force as a magnitude times some arbitrary direction, calculate the dot product of that force into that direction. Well, F dotted into its own unit vector is the magnitude of that dot that. The cos of the angle between these two things is going to be 1. So a force dotted into its own unit vector gives its magnitude back, right? So a force dotted into its own unit vector gives its magnitude back. So that might be a quick way of calculating the magnitude if you already know the unit vector. Now, here's a force. Here's an arbitrary direction. Bit in the x direction, bit in the y direction, bit in the z direction. Square and add all these components to check that this is a unit vector. It is one. Using the dot product, calculate FA, the component of F in the A hat direction. That is just F dot A. And you can use the formula to work that out. F dot A is the modulus of this one. Well, that's the magnitude of that force. The magnitude of this one, well, that's 1. And the cos of the angle between them. So it's just the magnitude of this, the cos of the angle between them. It is the amount of this force in the direction of A. F dotted into a unit vector gives that. And so we can do that dot product, right? It's 3 times that, 5 times that, 7 times that. Add them all together. Newtons comes out the end. And there we go. The amount of force, this force in that direction is 9.051 newtons. Things to note here is that that component is the component of the force in that direction. Only that direction. F, though, is in 3 dimensions, right? If you were to work out the magnitude of this force, it would be greater than this. So that means that there is some force in the other 2 directions, potentially directions that are perpendicular to this one. Just like we've got X, Y, and Z, we might have 3 other perpendicular directions. But whatever that direction is, FA is the amount of this force in that direction, so long as it's a unit vector. And just to reiterate here, unit vectors, i.e. directions, don't have units. Only components and magnitudes carry units, i.e. the scalar part. So that's why this has units and this doesn't. This doesn't even have meters, it's just a direction. It's a unit vector. So now I've given you another vector. It's just the minus of the previous one. So the amount of that force in that direction we might expect is the negative of what was in the other direction, because it's just minus in every bit. So FB is negative, which means that the force is acting in the opposite direction to the unit vector direction. So we've got a direction here, we've got a force here, and because this is negative, the amount of force in that direction is minus, which means it's in the opposite direction. That's going to be super important in electromagnetism. Electric charges have positive and negative signs defined precisely so that force is in the correct direction. So this idea of unit vectors is super important in mechanics and circular motion. It's super important in electromagnetism. So have a practice of this idea of unit vectors. So this is really the last bit, and I'm not really going to expect you to go through it. But why is this true in general? It was true for Cartesian coordinates. It was true because I and j and k are at right angles to each other. But this is kind of weird, right? Why is this generally the case? Easy to prove for Cartesian, trickier in general. Here's an optional task. If you're into maths, if you like maths, if you like things being rigorously proved, if you're doing theoretical physics, this might be something worth having a go at. proving the dot product identity in general. So not just for X, Y, and Z, but in general. So here we go. The task is using the law of cosines and the two vectors A and B. So the law of cosines is something that's a bit more general than Pythagoras' theorem. You can Google it, have a look at what it is. I want you to show that mod A, mod B, cos theta, so that's more than 3 dimensions now. We've got A1, A2, blah, blah, up to n, so it's an n-dimensional vector. B, B1, B2, blah, blah, Bn. The modulus of this times the modulus of this times the angle between them is equal to the sum from I equals 1 to n of AI, BI, where n is the number of components in the vector, and that's the law of cosines for an arbitrary triangle in some number of dimensions. So it's important that this means, I'm going to do this, by the way, you don't have to do this. If you want to do this, pause the video now and have a go. I reckon it'd take you like an hour to work it out, maybe 2. It's a hard problem. I'm going to go through it now. So unpause the video if you want to see the proof of this. But if you're not interested in all this math stuff, don't worry about it. All that matters is everything up to this point. Understanding how to represent a vector and how to use it in physics problems. But just for interest's sake, this sum means sum over all i's. In other words, sum of I from I equals 1 to n of AI, BI is A1, B1 plus A2, B2 plus A3, B3 plus A4, B4, blah, 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 all the way up to AN, BN. So this is like the general dot product, right, for more than 3 dimensions. Here's the law of cosines. So the first thing we might want to do is put all that vector stuff into use and say, okay, A is a vector, B is a vector, and because we now know how to take vectors from one another, this vector is A minus B. The cosine law says that the modulus of A minus B squared is equal to A squared plus B squared minus 2 mod A mod B cos theta. So that's the law of cosines right there. Google a proof for it if you want, but that is our vector representation of this. Rearrange it to get our dot producty bit there. Take that over to that side, take that over to that side, divide by 2. Mod A mod B cos theta, which we hope is going to equal this, is currently equal to a half. That times that minus that. Substitute those summations in, right? Because the modulus of A is the sum over all squares of all the components of A. So modulus of A squared is A1 squared, A2 squared, A3 squared, A4 squared. Add them all together. Same for this. And same for this, right? A minus B squared is A1 minus B1, all squared, plus A1 minus A2 minus B2, all squared, plus A3 minus B3, all squared, sum over all of them. Expand it, so we'll pull that summation out, expand these brackets as AI squared plus BI squared minus 2 AI BI. We've got an AI here, a BI here, one there, one there. That's going to be interesting. Cancel, 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 cancel. That minus cancels with that minus. That half cancels with that 2. There we go. That's the proof. That is why A dot B, mod A mod B cos theta, in general, is the sum over all of the products of components. In 3 dimensions and Cartesian coordinates, though, we've seen why that is the case. So that's the end of this one. Hope it's been useful. Have a go at those tasks, except the last one, which is optional. But practice, understand what a unit vector is, understand what a vector magnitude is, understand how you can write vectors as x and y components, and understand how to add them, subtract them, and multiply them by scalars and do the dot product. If you've got all of that, you're ready for the first half, 3/4 of my mechanics course for Year 1 physics. Thanks a lot. See you in the next one.